Howdy gang, welcome back to Calc 2. Today we're going to continue talking about convergence in the setting of improper integrals. So I want to make sure you're all very comfy with that stuff. Then the new thing we're going to introduce this week is sequences. So the meat of the topic today is going to be our second big convergence area. Yeah, we'll start. No, I don't know how much we really did cover all of improper integrals, but I wouldn't mind looking at one or two little problems there before we move on. Today's the 23rd. And today I'll do a couple fun improper integrals. And then we're going to start talking about sequences, which is section 11.1. So the here we go. All right. I would be happy to take any particular problems that you guys want to see from the homework. There are a few fun ones in there. I've got one in mind that I would like to show you that is not in the homework. But I've had a number of folks come by office hours talking about improper integrals, and I just want to make sure you guys are really comfy with this stuff before we move on, because they're kind of the easiest of all the convergence type things we'll be doing. So I think it's a wise move to get 100% comfortable with them before moving on to sequences, which are a little tougher, and then series, which are considerably tougher. So I would not mind opening the class with any requests. Are there any problems from, what is it, homework 6 that you guys would like to see? Any of the improper integral problems? Well, you're letting me know in chat what you want. Oh, I've got them right here. Yeah, okay, they're all up. Okay.
Yeah, it may be hard just right now because all of the homework deadline is closed off. So unless we got extension requests, we can't really see the problems.
Oh, that's right. Yeah, all right. Well, let me do it like this. Let's stay signed in. Schedule this. Oh, no, that's homework 7. Let's get the group. Yeah, you let me come in here. I'll just give you guys until midnight tonight or something as the default on homework 6. That way we can fiddle around. Schedules. Well, how about this? Let's do it 10 hours after today's class. All right. That's plenty of time for us to get in there and take a look at a few things. So yeah, is there anything from homework 6, which I have right here, that you guys would like to look at?
I had a lot of trouble with the problems that were like, for what value of P does this diverge versus converge? Yeah. And it got to questions where it was like the denominator was x times ln of x to the power of P.
I would be happy to work this one out. Yeah, 26 is very good. 25 is also fun. I want to point out here that you cannot use that 25 is not a P integral. And I'd like you guys to tell me why is 25 not a P integral?
Because it has a 30. Oh, wait, it's just from 0 to 1.
Yeah, that's the big issue, right? Yeah, this is a type 1, this is a type 2 integral, not a type 1 integral. We can pop the 33 out. So let homework problems. Number 25 asks you to find values of P for which integral 0 to 1, 1 over x to the P dx converges. And I want to make the note here, integral 0 to 1, 1 over x to the p dx is not a p integral. P integrals are of the form integral 1 to infinity, 1 over x to the p dx. And anything else ruins the p-ness. I know that that's a really bad joke. I feel guilty every time I make it, but it seems to help. So, yeah, anything other than a 1 here, an infinity here, a 1 over x to the p here, or a dx here ruins the p-ness of the p integral. So specifically, if this is a type 2 integral, not a type 1 integral. The type 1 integrals are p integrals. So this one you have to attack directly. And if you haven't solved this to your satisfaction yet, and I strongly encourage you to do that because problems like this will show up on the exam, I recommend for this problem, first, look at some examples. Like p equal to 1/2, p equal to 1, p equal to 2. These would be a good first few to try. So like integral 0 to 1, 1 over x to the 1/2 dx, integral 0 to 1, 1 over x dx, integral 0 to 1, 1 over x squared dx. Solve each of these carefully. This first guy would be lim r to 0 plus integral r to 1 x to the negative 1/2 dx. And this next guy would be lim r to 0 plus integral r to 1. Just leave it as 1 over x dx because that's the nice form for his antiderivative. And this guy would be lim r to 0 plus integral r to 1 x to the negative 2 dx. I'm not going to crunch each of these out, but if you haven't solved this problem to your satisfaction yet, I encourage you to do each of these and then form an hypothesis and try to prove it. It's not a terribly difficult thing to come up with. I'm sure many of you already have solved this problem, but if you have not solved this problem, this would be my recommendation. You'll notice here, I'm taking p to be 1/2, which is smaller than 1. Here, I'm taking p to be exactly 1, which was an important boundary value for p in the original p integral thing, so maybe it's an important boundary value here. And here I'm taking p to be strictly larger than 1. So I would recommend you take 1 from each of those categories. And then when you try to prove whatever your hypothesis is, consider those 3 cases separately: p less than 1, p equal to 1, and p greater than 1. None of these are terribly hard, and we've already done this one and this one in class, if I remember right. So you can look back at previous videos if you want. That's all I'm going to say on number 25 here. If you haven't gotten this done, I did add 10 hours to that, so you can work on this homework up to pretty late tonight, around 10 p.m. if you want more time to do an extension request. But yeah, this is a good one. The other one that's kind of like this is number 26. And there is a really slick solution to number 26 that I'm excited to share with you guys. And that's the same sort of thing. For what values of p does integral e to infinity 1 over x times the natural log of x to the p dx converge. Sure. So the way we get started here, we're just going to crunch this out, right? We're just going to do the computation. So the integral from e to infinity, 1 over x times ln x to the p dx. This is lim r to infinity, integral e to r, 1 over x ln x to the p dx. I'm being a little bit lazy. Usually I like to put the inside of the natural log in parentheses like I did here. But there's just a lot of parens there, and I know you guys all know what I mean by this. The move to solving this integral is a substitution, right? I've got like a 1 over x here, which is the derivative of ln x. So I'm going to make the substitution u or z equals ln x, because then du is 1 over x dx. The other thing I need to do is change my bounds, and I need to be really careful about this. So you can't make this substitution until you've written this as a limit. That's something we talked about last week, right? U sub, IBP, all that shit only works for Riemann integrals. And until you rewrite it as a limit, you're not actually looking at a Riemann integral, which means your upper bound here has to be an R. Now, when x is equal to e, u is the natural log of e. What is the natural log of e? Yeah, it's 1. And when x is equal to r, u would just be the natural log of r. So I get lim r to infinity integral 1 to the natural log of r. 1 over x dx is du. And the only other thing that's there is 1 over ln x to the p. Well, that's 1 over u to the p. So I have 1 over u to the p du. One way of finishing the problem from here is to consider 3 cases: p less than 1, p equal to 1, and p bigger than 1, and then to crunch out your antiderivatives. But there's a much smarter solution. As r goes to infinity, the natural log of r goes where?
To infinity as well.
Also goes to infinity. So I can rewrite this integral back as an improper integral. I can say, okay, if I take the limit here, it's kind of it seems like it's going backwards, right? It seems like we're kind of undoing what we did going from here to here. But we rewrite this as a limit so that we can make this substitution. And then once we've made the substitution we get here, we can go back to writing this as an improper integral, integral 1 to, well, ln r, as r goes to infinity, that goes to infinity. And now this is just 1 over u to the p du. Why is this a smart move? What kind of integral is this?
Just a p integral?
Yeah. And we know everything there is to know about p integrals.
If p is positive, well, if p is greater than 1, then it converges.
Good. And diverges if p is less than or equal to 1. And since this integral is equal to the original integral, right? Original integral equals this integral. If this integral converges when p is bigger than 1 and diverges otherwise, then this integral converges if p is bigger than 1 and diverges otherwise. So we're done. This is a nice, slick argument that doesn't require actually doing the computation. Now, I think the problem does ask you to compute this integral, but you can do that in terms of the p integrals. Again, we did the p integral calculation last time in class. I told you what those converge to. So you know what the value of this integral is. If you've forgotten, look back at the notes from last time. That's, I think, 1 over 1 minus p, if p is larger than 1. Or maybe 1 over p minus 1. I don't remember, one of those two. But yeah, this is the slick solution to number 26. You can first rewrite as a limit. That allows you to do the u sub. Having done the u sub, you kind of examine the integral you get and you go, shit, this looks a lot like a p integral. I wonder what happens if I try to rewrite this guy as an improper integral again. Since this goes to infinity as r goes to infinity, you can rewrite it as the improper integral from 1 to infinity of 1 over u to the p du, which is indeed a p integral. So that is the slick way to do this.
So how would the syntax of our answer follow? Like, I'm a little unsure on that.
Well, this is it. This is it. So the integral converges if p is greater than 1 and diverges if p is less than or equal to 1. So I think maybe
Can we just write like therefore within
Yeah.
like the little answer box?
Yep. Well, so what did they allow for here? I think they say here, find values p for which the integral converges. So you just say p is greater than 1 here. And then here, here you'd have to tell them what the value of the integral is for those values. So you'd have to figure out what this integral comes out to, which you can do a number of ways. You can assume p is bigger than 1 because you know that's where the thing when the thing converges, and then do the computation. Or you can fall back on the computation we did last time. Where
Does it matter which value of p that you choose? Like if I just arbitrarily choose 2, is it going to work out the same?
No. So it's your answer is going to be a function of p. Right? At the end of this, you're going to have p's in it. So the answer that goes here is definitely going to have p's in it. Sorry, the answer that goes here is going to have p's in it.
All right. Well, that's a little confusing, but I'll work it out.
These are tricky, but these are really good problems for getting your brain to think in the way we want them to start thinking in preparation for a series. So Daniel asked to see number 6 also, so let me move back up here to number 6. Oh, this is fun. Yeah, so this is all just about the antiderivative of a non-natural exponential. So homework 6, problem 6. And then there's one other I'd like to look at here. They just want us to evaluate the integral from negative infinity to 0 of 5 to the x dx, right? 5 to the r dr. Whatever, I'll write it with x's because I already wrote it. The trick is, well, there's no real trick here. So this is just, we write as lim r to negative infinity, integral r to 0, 5 to the x dx, or 5 to the r dr. And then you need to remember what an antiderivative for 5 to the x looks like. I put this on an exam once, and I realized that Calc 2 students do not remember how to antiderive other exponentials. So I think it might be worth saying, I'll just show you what you get here. This is 5 to the x divided by the natural log of 5. This is evaluated from, from r up to 0. The rule, the thing that's running in the background here, remember that the derivative d dx of another base exponential b to the x, this is b to the x times the natural log of b. So the antiderivative of b to the x dx is going to be b to the x over the natural log of b, and plus c if we're doing it as an indefinite integral. So this is really all we need, but it's something that people forget. Of course, b is a constant, so the natural log of b is a constant. Down here, the natural log of 5, that's just a number. It's just a constant. It doesn't have any x's in it. So he can pop all the way out if you want. This would be 1 over the natural log of 5 times lim r to negative infinity 5 to the 0 minus 5 to the r. Which is 1 over the natural log of 5 times 5 to the 0 is 1. What does 5 to the r do as r goes to negative infinity? What is 5 to the negative infinity?
Zero.
Yeah, good, it's 0. If you want to think about it a little bit more carefully, if it's not obvious right away to you, this is 1 minus 1 over 5 to the positive infinity. And you take 5 and raise it to a big number, you're going to get a big ass number. So that's 1 over infinity there. This is 1 over the natural log of 5 times 1 minus 1 over infinity. That's just 1 over the natural log of 5 times 1. So this one's not too bad, but you do have to remember this antiderivative formula that people tend to forget. Both of these you really should remember. Both of these are important. You can think of the natural exponential e to the x as a special case of each of these, right? The derivative of e to the x is e to the x times the natural log of e. It's just that the natural log of e is 1. Or the antiderivative of e to the x is e to the x divided by the natural log of e. It just happens to be the case that the natural log of e is 1. All right. One more problem I wanted to look at. There's actually a couple that are kind of like this, but let me see.
Is number 9 IBP?
No, yeah, I'm glad you asked. This is actually the one I was thinking of doing. Let's do it. I'll do a slightly different version, but yeah. I'm going to do 1 to infinity. Yeah, we don't need any IVP here, but if I integrate 1 to infinity, e to the negative 1 over x divided by x squared dx, right? Yeah, okay. So as always, we need to begin by writing this as a limit. Integral 1 to infinity, integral 1 to r. So integral 1 to infinity becomes limit r to infinity integral 1 to r. And then I've got my e to the negative 1 over x, and I'm dividing that by x squared. So that's the same as multiplying by 1 over x squared, like this. Handful of ways to attack this from here. My advice would be the following substitution. Z equals 1 over x, or even negative 1 over x. Substitute for the inside function here, the exponent. dz is then the derivative of 1 over x. That's positive 1 over x squared. That's exactly what we have sitting over there. And then the bounds change, of course. When x is equal to 1, z would be negative 1 over 1, which is negative 1. And when x is equal to r, z would be equal to negative 1 over r. So you get here lim r to infinity integral negative 1 up to negative 1 over r e to the z dz. And there's lots of ways to skin this cat. The reason I like this example is because the substitution does something very special. Remember what we did with number 26? So first, are we comfy here? Are we comfy up to this step? Any questions up to this step? Okay. Remember what we did with number 26? After we made a little u sub, we asked, oh, well, what does this piece do as this piece goes to infinity? And that let us rewrite our integral as a p integral. This substitution allows us to do something similar. As r goes to infinity, negative 1 over r goes where?
Zero.
Yeah. So the above line is equal to integral -1 to 0, e to the z dz. This substitution makes the integral no longer improper. Isn't that cool? Now you don't need to do it like this. You could just go ahead and write down your antiderivative, plug in those bounds, and then take the limit. But I think this is a cool observation that when you make this substitution, it takes the improper integral and turns it into a proper one. That's a very cool substitution. And I would love it if you guys could see this in the context of this thing I posted to the modules a long time ago about why we change bounds in u sub.
Can we do that for every problem? Like when we change the bounds, can we look at our limit and see if we can change it?
Yeah, it's
Like
always
make it
worth.
equal to 0 or infinity?
I think if it was infinity and it's going to stay infinity, then there's no sense in rewriting it like that unless the integral becomes something like obvious, like a p integral. So most of the time, if the bound was infinity and it's going to stay infinity, you should just leave it as a limit. But this special case here where the bound was infinity and after changing your bounds, the limit becomes 0, then that's really something like this going on. Remember when we talked about why we have to change bounds, right? And the area under the red curve here from 0 to 0.5 is the same as the area under the blue curve here from 1 to 1.5. That's just a shift. But that's just a shift because the substitution that was made here is just u equals x minus 1, which is a shift, right? It just drags everything to the right by 1 unit. But if you make a substitution like u equals 1 over x or z equals 1 over x, that substitution does something funny with the x-axis. It stretches it out in some parts and it compresses it in others. So there's a video I'd like to share with you here. Functions as transformations. Linear transformations. This isn't what I wanted. Oh, fuck. I don't think this is what I needed. I'll see if I can find it. The basic idea is that this substitution right here stretches out the x-axis near 0 and compresses it as you go towards infinity. So it takes the area underneath this function from 1 to infinity, and it makes it the same as the area under this function from -1 to 0. It's a very strange thing, but the algebra makes great sense. This piece goes to 0 as r goes to infinity, so we end up with this. And the miracle is that this is no longer improper. So sometimes a substitution has the ability to take an improper integral and turn it into a proper one. And now from here, this is an integral I could give to any Calc 1 student. They wouldn't be afraid of this. From here, we just take our antiderivative, which is e to the z, and evaluate from -1 to 0. So you get e to the 0 minus e to the negative 1, which is 1 minus 1 over e. So the integral 1 to infinity e to the negative 1 over x divided by x squared dx converges to 1 minus 1 over e. These are very cool. Substitutions that do this are going to be, if your original integral is a type 1, and the substitution you're making, the function right here, has a horizontal asymptote, which is finite. Anything like that, like z equals inverse tangent of x, would also do this. Z equals 1 over x squared would also do this. Transform a type 1 integral into a non-improper, a regular proper integral. Very, very fun stuff. And I just wanted to share with you guys some of the cooler things that can happen here. You're always safe to just dive in from this stage and do the obvious thing, right? Find an antiderivative, evaluate between these bounds, and then take the limit. But sometimes a step like this can be very insightful. It can help you see things that you otherwise wouldn't see, like on number 26, where we were able to see, oh yeah, this is a p integral now, so I don't have to do as much work. Okay. Was there anything else I wanted to talk about in here? There's some PFD stuff, there's some IBP stuff, some comparison stuff. We did some comparison problems the other day. I'm not too stressed. I think we're pretty good here. So yeah, I am going to transition now to talking about the new material. If you do want to see more examples of this work, or if you're struggling with something, please come by office hours. I'm more than happy to work problems with you guys there. But now for the new material today, we are going to begin section 11.1, which is on sequences. And there's only one place to begin in mathematics. That's the definition. A sequence is a function whose domain is potentially a subset of the non-negative number integers, which I call the natural numbers. Some people disagree with me on this. Some people would say 0 is not a natural number. But we're going to do things the French way. We're going to say 0 is a natural number. The symbol I'm using here is a blackboard bold N, just means natural number. And for us, the range or codomain of this function, of any such function, will be the real numbers. So that's all. The notation we use for sequences is a little different. Instead of writing like f of x equals 1 over x to describe the sequence 1, 1/2, 1/3, 1/4, and so on. We would write something like f of n equals 1 over n, or really, the notation you're going to see is an equals 1 over n. So I'm just trying to introduce the little bits of notation one thing at a time. We use the variable n instead of the variable x because the variables here are only allowed to represent whole numbers. And instead of using like the function notation f of something, We use the subscript notation, a sub something. Why is a good question. Computer programmers use this a lot. They still use the function notation. Sometimes they use a square bracket here instead of parentheses. But mathematicians really like the subscript notation for reasons that will hopefully make sense eventually. So to describe the sequence whose terms are 1, 1/2, 1/3, 1/4, and so on, I would write an equals 1 over n, and say that n begins at 1. Or, I know there's a lot of notation, curly braces 1 over n equals 1 to infinity. So sort of one of these. They give you the algebraic representation, right? They tell you the function algebraically is 1 over n, the reciprocal function. And it also tells you the explicit domain, because with sequences, it's not clear whether you start at 0, 1, 2, 3. I cannot start this sequence at 0, of course. 1 over 0 is undefined. The notation on the right is, of course, more compact. But what it doesn't do is it doesn't name the sequence. It doesn't give the sequence a name like an, like f of x. So you'll see both of these. All right. Let's look at some examples. Of course, there's the 1 over n sequence there. Another example would be the sequence of squares, an equals n squared. And here I could have n starting at 0 if I wanted. The first few terms of this sequence are, well, they told me that n is starting at 0. So the first term is a0. And please be careful with the language here. Don't call this a to the 0. It's not a to the 0. That sounds like you're raising something to a power. You can read it as a0 or a sub 0 or even a of 0. All of those are fine, but please don't call it a to the 0. This would be 0 squared, which is 0. A1 would be 1 squared, which is 1. A2 would be 2 squared, which is 4. A3 would be 3 squared, which is 9. A4 would be 4 squared, which is 16. A5 would be 5 squared, which is 25. And you could continue like this if you wanted. So sometimes people will refer to these as infinite sequences, but that's, it's the only sequences we're interested in are infinite ones, so it's a little bit redundant. You can graph a sequence, just like you graph any other function, as ordered pairs, input, comma, output. So let me show you what the graph of this sequence looks like. I'll mark off here 1, 2, 3, 4, 5, 25 there. 25, so half of this would be like 12.5, so 16 should be like here. 9 would be So the first ordered pair that's on my graph is 0, 0. When n, so this is my n axis, and this is the graph y equals an. 0, 0, because when n is 0, the output is 0. 1, 1 would be on my graph, because when n is 1, the output is 1. So that's here. 2, 4 is on the graph. 3, 9 is on the graph. 4, 16 is on the graph. And 5, 25 is on the graph. Well, this is what the graph of this sequence looks like. It's just some dots. So a little note here, the graph of a sequence is a collection of dots, which are ordered pairs of the form n, an. So it's just like graphing any other function. A point is on the graph if the input and output pair comes from the relation. So like when I feed this the input 0, I get the output 0. That's why 0, 0 is on the graph. When I feed this sequence the input 3, I get the output 9. That's why the ordered pair 3, 9 is on the graph. There is no curve. There is no point like in between here on this graph. There's no point in between here on the graph. There's no point in between here or in between here. Because the domain of the sequence is just the whole numbers. Okay. There's some other examples. There's a bunch of stuff to say about sequences. Yeah, let's look at some shit like that. We'll get there eventually. That's a little too much. Okay. So let's find the first few terms and sketch the graph of the sequence an equals -1 to the n plus 1 over n, where n is greater than or equal to 1. All right. Well, let's find the first 5 terms. Okay, what's a1? N starts at 1, so a1 is the first term. That would be -1 squared over 1, which is 1 over 1, or just 1. A2 would be -1 cubed over 2, which is -1/2. A3 is -1⁴ over 3, which is +1/3. A4, that's -1⁵ over 4. That's -1/4. And A5, the fifth term, would be -1⁶ over 5, which is +1/5. And if I want to draw the graph, so something like this. I'll mark this up here as +1 and this down here as -1. So A1 is 1, which means the ordered pair 1, 1 is on my graph. A2 is -1/2. So that's like here, 2, -1/2. A3 is +1/3. That's like here. So A3, 3, A3 would look like this. A4 was -1/4. That's halfway between -0 and -1/2. So that's like right here. And A5 is +1/5, which is going to be like about that high. That's like right here. And the big thing with sequences is to kind of recognize a pattern and start trying to extrapolate. All right. And I see a pattern here. Every other term jumps from being positive to negative, positive, negative, positive. So if even without the algebra, if you just gave me the graph, I would guess that the next point on the graph is like right here. And then the next point after that would be like right here, getting closer and closer to the x, or I should say n axis. And jumping up and down from above to below to above to below. Nope, sorry, no, what is this? This is 1/3. This is 1/5. This is 1/5. Oh, I got a cat fight going on out front. Okay. Here. Sorry guys, give me just 1 second. Yeah, I did that too. Where's your sister? No, come here. No, home. Right now. Now, get in here. Get in. Sorry about that, guys. There's a very friendly neighborhood feral that's been hanging out in her yard, and I think my cat just decided to tell her that she does not live here. Anyway, this is the graph of this sequence. Any questions on how we got these terms or how we graphed them here? Okay. So all the normal calculus stuff, like continuity and differentiability, don't really apply to a sequence, right? If the graph of a sequence is just a collection of dots, then there's no way to say that this is continuous. Since the graph of any sequence is a collection of isolated dots, we can't really talk about continuity, right? There's no way, certainly this is not the graph of a continuous function, right? You have to lift your pen to draw this graph. And that means, so differentiability is automatically out. Right? Because in order to be differentiable, you have to be continuous. So what sort of calculus operations are we going to do? So how is this a calc thing? What sort of calculus operations could we hope to do with these? Like, I can't talk about the limit as n approaches 3 because n is only allowed to be a whole number. So I can't ask, like, as n gets closer and closer to 3, what's the graph doing? It's just like there's this dot here and there's nothing else. Limits.
Convergence you could talk about.
Yeah, a specific kind of convergence. Limits at any finite n value are also out. But I can ask about limits as n goes to infinity. And it turns out there's a notion of integration for sequences as well. They're called series. A series is the integral of a sequence. But before we even introduce the concept of a series, I need to get you comfortable doing this. This is going to be our big calculus operation for sequences. We're going to take limits as n goes to infinity, and that's how we're going to define convergence for a sequence. All right. So let's do it. I'm going to go ahead and show you the definition of the limit as n goes to infinity for a sequence, and along with that will come the definition of convergence for a sequence. This is your second notion of convergence. You have a notion of convergence for improper integrals. Today I will give you a notion of convergence for a sequence. Down the road I will tell you what it means for a series and a power series to converge. They're totally separate things. Don't confuse them. They kind of look very similar. They have a lot of the same symbols and a lot of the same language. So it's very easy to confuse them, but please try really hard not to. This is why I recommend having a few separate dedicated pages in your notes to convergence results for integrals, convergence results for sequences, convergence results for series, so that you can keep them separate and have a place to reference them. So the main thing we're going to talk about here is the limit of a sequence. There's only one limit we can talk about, and that says n goes to infinity. So I'm just going to refer to the limit of a sequence, and without ambiguity, you'll understand that I mean as n goes to infinity. We say that the limit as n goes to infinity of a sequence an is equal to L if, and I'll give this to you a few ways, as n gets bigger and bigger, an gets closer and closer, and here's the important part, and stays close to L. This is the intuitive definition. Slightly less intuitive, but slightly more rigorous. We say that the limit as n goes to infinity of the sequence an is equal to L if we can make an arbitrarily close to L by taking n to be sufficiently large. And then finally, we've got the whole hog definition. We say when n to infinity an equals L if given any positive number epsilon, we can force the absolute value of an minus L to be less than epsilon by taking n sufficiently large. Say n bigger than some capital N. I'll just call it capital N. All of these say the same thing. The first one is the one that you're going to have in your head. The bottom one is the one that you use if you want to prove shit. We won't be doing much proof in this class, but if you ever take a class in real analysis or a class that gets more rigorous, then you will need that bottom definition. The picture, and there is a nice picture here, looks like this. I have some sequence and I suspect it's converging to some number L. So let me do my best to draw this for you. To say that the limit of my sequence is L means that the dots that form the graph of the sequence get closer and closer and closer and stay close to L. That's all. I don't care what they do at first. They might jump around quite a bit. But as long as past some point, they stay very close to L, I am happy. The way we make that quantitative, does this blue actually work? No, does this blue actually work? Kind of, okay. Is that we give ourselves some epsilon window about L. And we say, okay, well, past some point, do the terms of my sequence all live within that epsilon window? If they do, and this is true for any epsilon, so this would be L minus epsilon, this would be L plus epsilon. Here would be the capital N, right? If you look before this point, this guy and all the others are outside the epsilon window. But if you look from here on, all the terms of the sequence are within this little blue window about L. So the distance from AN to epsilon, which is the vertical distance, the distance from AN to L, which is the vertical distance from the orange here in the middle to the blue, can be made small by taking n sufficiently large. So here's the black and here's the orange. So the distance from AN to L here is this distance. From AN to L here is this distance. From AN to L here is this distance. As long as all of those distances are smaller than epsilon, when you go past a certain point, then that's what it means to say that the sequence is convergent. That's what it means to say this inequality is satisfied. And this inequality needs to be satisfied for any epsilon. In other words, what we're talking about here are horizontal asymptotes. Kind of the silly way to say this is we could say that the line y equals L is a horizontal asymptote for the sequence AN. That is also equivalent. All right. Your book draws this picture, and they probably draw it a little bit better than I do, so I'm going to show you the picture in the book. Here you go. So here's the terms of your sequence, and as you run off to the right, they are getting closer and closer to the horizontal line y equals L. Here are the terms of your sequence, and as we run off to the right, they're getting closer and closer to the horizontal line y equals L. And here's their definition, right? They say the limit as n goes to infinity of an equals L if we can make an as close to L as we like by taking n sufficiently large. Now here's the definition of convergence. The sequence AN is called convergent if the limit as n goes to infinity of AN exists and is finite. In other words, i.e., when n to infinity AN equals L for some real number L. We call L the limit of the sequence, right? So a sequent is convergent if it has a finite limit. If the limit as n goes to infinity of AN does not exist or is not finite, then we say the sequence AN diverges. Again, this is your second notion of convergence. A sequence, and generally, by the way, when we want to refer to the sequence as a singular noun, we'll put it in curly braces like this. So if I'm being careful with my notation, this is how I should write it. The sequence AN is called convergent if the limit as n goes to infinity of the ANs exists and is finite, i.e. lim n to infinity AN equals L for some real number L. Note, infinity is not a real number. Right? Infinity is not a number. If the limit of the sequence does not exist or is not finite, then we say the sequence AN diverges. So some examples. I can take some of the things we played with a minute ago, right? The sequence AN defined by the rule AN equals n squared, where n is greater than or equal to 0, has lim n to infinity AN equals lim n to infinity of n squared. And as n goes to infinity, n squared goes to infinity. This is, you can be silly about it and call it infinity squared, which is infinity, which is not finite. Thus, we say this sequence diverges. Another example we played with. The sequence AN defined by the rule AN equals 1 over n, where n had to be greater than or equal to 1. He has limit lim n to infinity AN equals lim n to infinity 1 over n, which is 1 over infinity, which is 0. 0 is a finite real number. So this sequence, which I'll say which is finite, thus we say this sequence converges. And I can hear anybody who's taken Calc 2 in the past having a little bit of an aneurysm right now, because we associate often 1 over n with the word diverges. But I'm talking about sequences here, not series. So if you've never seen this shit before, don't worry. But trust me when I say there is room for confusion down the road with these different notions of convergence. The sequence 1 over n is definitely convergent as a sequence, because the definition of convergence for a sequence is just having a finite limit. You guys with me so far on these two examples? Are there any questions about these or the definition of convergence for a sequence? Hamlet, be good, Bubba. It's okay, you can do this. Know him. All right, so obviously limits at infinity are going to be a big deal in this section. I warned about this last week. They're going to be a big deal all through the middle part of this course. If your skills with limits at infinity need some sharpening, it is past time to sharpen them. You need to start sharpening them immediately. They need to be good. So I will look at some more examples with you guys. There are some theorems we need to look at, but I think maybe first it's worthwhile to just take a look at one or two examples that are not difficult, that are things you could have done in Calc 1. Here's the picture with the epsilon windows, right? And the idea is if you really want to understand this stuff in a deep way, you think about this green window as shrinking, kind of pinching in. And as long as all but finitely many of the terms are trapped in the window, we're good. All right, so these are lots and lots of theorems, which we will get to. Before I start looking around at those, let me look at two of these. Yeah. So just for practice, this is mostly about algebra. Find the limit as n goes to infinity of n over n plus 1. How do I do this? Those last two problems, I just kind of plugged in infinity and everything worked out. What happens if I plug in infinity here?
It's undefined.
Yeah, I would get infinity over infinity, which is an indeterminate form, right?
Do we do LHOP?
Well, let me address that in a second. Yes, you could use L'Hopital's rule, but you don't want to use L'Hopital's rule unless you need to. And there are some subtleties here that kind of fuck things up. Like this is not a differentiable function, right? These are sequences. It's not smooth. So this concept of a derivative really doesn't make sense here. L'Hopital's rule can be applied, but you kind of have to wander through a connection to a smooth function first. I'll show you that connection. It is manageable, but there's a much better approach. When I teach this, I call it renormalization, and I teach this in my Calc 1 class. All Calc 1 classes are supposed to teach this. This is the renormalization trick. You divide top and bottom by the fastest growing term. So upstairs, I've got an n, downstairs, I've got an n. The fastest growing term here is just n. So the clever way to handle this is to divide top and bottom by n. So I have lim n to infinity, n over n plus 1 is equal to lim n to infinity, n times 1 over n divided by n plus 1 times 1 over n. I'm going to divide top and bottom by n. N divided by n upstairs, so I still have lim n to infinity. You need to be disciplined about this. Keep writing your limits, write your equal signs. Don't be sloppy. The notation here matters. It matters so much. And if you get sloppy here, it's going to fuck you really hard when we start talking about series. So please start practicing this discipline now. N divided by n upstairs here is just 1. And downstairs, when I distribute this, I'll have 1 plus 1 over n. All right, if you divide every term here by n, you get 1, 1, and 1 over n. Now, as n goes to infinity, this is 1 over 1 plus 1 over infinity, which is 1 over 1 plus 0, which is 1. Making sense?
What would be a different function where like the fastest growing term is not just a variable or just n?
Yeah, so let's look at some other stuff. So here, the fastest growing term in the top is n squared. The fastest growing term in the bottom is n squared. So if I divide top and bottom by n squared, I'll get 2 plus 3 over n minus 7 over n squared, all divided by 5 plus 2 over n squared. Right, just dividing every term here by n squared. Now this piece is going to go to 3 over infinity. So my next line here would look like 2 plus 3 over infinity minus n squared. That's also going to infinity. Downstairs here I have 5 plus 2 over infinity. And 3 over infinity, 7 over infinity, 2 over infinity, those are all 0. So this is 2 plus 0 minus 0 over 5 plus 0, or just 2/5. You guys remember that rule from pre-calculus for finding horizontal asymptotes where you take the ratio of lead coefficients? This is how you prove that. This is where that comes from. It's the renormalization trick. And it can be applied to other things too, not just rational functions. I'm going to hold here for just a second, and then I'll look at a couple of slightly more exotic examples. All right. What if I just want to compute this? I can't distribute the square root. That doesn't work, right? We saw that when we talked about integrals. Distributes don't square roots don't distribute over addition or subtraction. So upstairs, I have the square root of 3n squared plus n, and downstairs I have n plus 4. There's no way to clean this up algebraically that's really nice. But downstairs, my fastest growing term is n. Upstairs, my fastest growing term is n squared, but it's under a square root. So I think of the sort of fastest growing term here as being n. The top and bottom grow at similar speeds. There's a quadratic here, but it's under a root, so the kind of overall speed of the numerator is still growing like n. So I would do the same sort of shit here. I'm going to divide top and bottom by n. But there's some algebra trickery that's required to figure out what happens in the numerator.
Will we run into problems if we pick the wrong fastest growing? Like, are we just gonna come to a dead end and then realize we picked the wrong one and then just try
Basically.
another one?
Yep. Yeah, if you were to say try to divide top and bottom by n squared here, what you'd find is that your bottom the big bottom here is going to go to 0 after distributing and everything, and you'd be like, well, that's not helpful. I can't tell what's going on. So if you choose the wrong thing to divide top and bottom by, it will make itself known. But you might have a little bit of work between when you make that error and when it shows up, or when it shows itself to have been an error. The necessary trick here is that I need to get this piece into the square root. So to do that, we rewrite it as, instead of 1 over n, I could say that's the square root of 1 over n squared. And you may remember this trick from Calc 1. This is something that you're supposed to learn back in section 2.6. But it's usually talked about for a few days and then you never see it again. So it's also understandable if you've forgotten it. Downstairs, I'm not doing anything with this stuff. So I divide top and bottom by n. Upstairs, I want to get this piece to interact with these pieces. To do that, I need to get it under the radical. To get it under the radical, I need to write it as the square root of something. Well, 1 over n is the square root of 1 over n squared. There's some stuff with absolute values here that I'm kind of ignoring, but n is going to infinity. I'm only interested in n being positive numbers, so I don't even have to worry about that. From here, it's just algebra as normal. Still writing my equal sign, still writing my limits. The square root of this times the square root of that is one big square root with 3n squared plus n times 1 over n squared inside. That's just an algebra rule. And then down here, I still have n plus 4 times 1 over n. The algebra rule running in the background there is that the square root of a times the square root of b is the same as the square root of a times b. Square roots do play nice with multiplication, just not with addition or subtraction. Now I can distribute my 1 over n squared here, my 1 over n here. And I get limit n to infinity, square root of 3 plus 1 over n divided by 1 plus 4 over n. So as n goes to infinity, this becomes the square root of 3 plus 1 over infinity divided by 1 plus 4 over infinity. 1 over infinity and 4 over infinity are both 0. So this is the square root of 3 plus 0 over 1 plus 0, which is just the square root of 3. So this sequence, if I wanted to now practice my language stuff, I would say, therefore, the sequence an defined by the rule an equals the square root of 3n squared plus n over n plus 4 converges to the square root of 3. All right. So taking limits with tricks you learned back in section 2.6 of Calc 1, still very useful here. I want to address the original suggestion, which was to use L'Hopital's rule. We can do it, but we have to, like I said, kind of run around a little bit circuitously to get there. There's a theorem that we need. Now, remember when I said to set aside a few pages, one page for theorems relating to convergence of improper integrals, one page for theorems relating to convergence of sequences, one page for theorems relating to convergence of series. What I'm about to show you is the second thing that should go on your theorems related to convergence of sequences. The first thing should be the definition of convergence for a sequence, which is what we had. Where was it? Here, right? This should be the first thing on that page. The second thing that's going to go on that page is what I'm about to show you. Any questions on this before I move on? Daniel, you lit up for a second, but you're still showing as muted. Are you trying to ask something, buddy? You gotta.
No, I don't know what's going on.
All right. Okay, so here's our next theorem. This section has a lot of theorems. I'll refer this.
Professor,
Yeah.
I figured I will let you know the time. It's 1:58.
Oh shit. Damn. All right. Let's see. I got you guys from 12:30 to 1:45, so we're already over. All right. Next time we'll start on theorems. I'll leave it here then. That's a good start. Please read the textbook. I say this, right? You'll see that there's a boatload of theorems in here, definitions and theorems. The theorem that I was about to give you guys is this one. And then we're going to need to run through all of these theorems. So that's what we'll do on Thursday. There's many more. So yeah. Please read the section 11.1 in the textbook. 11.1 and 11.2, which we're going to save for next week. These are the most important sections in all of Calc 2. 11.1 and a thorough understanding of this is what you need to understand 11.2. A thorough understanding of 11.2 is what you need for all the rest of chapter 11. The rest of chapter 11, everything from the integral test through Taylor and Maclaurin series, is the reason Calc 2 has the reputation it does. Calc 2 has a reputation for being a fucking hard class. The reason is sequences and series. Integrals are tough, it's whatever, but not nearly as tough as series. So this is where things are going to get real hard. Please put the time in here and here so that this stuff is not so painful. We really need you to understand sequences, really need you to understand series. So please read 11.1 before class on Thursday. That way, as we go through these theorems, you'll have seen them before. They'll be a little bit easier to digest. And then next week, we're going to start on 11.2. Any burning questions before I let you guys go?
No, have a great day, Professor.
Alrighty, hang in there, guys. If you do have any questions, of course, you can come by office hours or send me a Canvas message or email. Otherwise, I'll see you all on Thursday.
All right. See you tomorrow, Professor. Bye-bye.